There are two objects in mathematics that seem as if they should have absolutely nothing to do with one another. The first is the Riemann zeta function, a complex function whose zeros somehow govern the hidden fluctuations of the prime numbers. The second is the octonions, an 8-dimensional number system so strange that multiplication is not even associative. So why would anybody place them in the same sentence? The answer I want to explore is not that somebody found an octonionic trick and suddenly solved the Riemann hypothesis. The connection is more geometric, and I think far more interesting. I have been developing a geometric framework called Zeta space. At its first genuinely 3-dimensional level sits a compact object I call the 3-seed, or S3. Its internal geometry does two things at once. First, it reconstructs the multiplication law of the octonions. Second, it supports the theta, melon, symmetry, and spectral structures from which the completed zeta function emerges. If that is right, the octonions and the Riemann hypothesis meet, because they are two shadows of the same underlying geometry. Let us begin with the familiar side. For real part of s greater than 1, the zeta function is the series. Zeta of s equals 1, plus 1 over 2 to the s, plus 1 over 3 to the s, and so on. Euler discovered that the same function can be written as a product over primes. That is the first miracle. One analytic object contains every prime number at once. Riemann then continued this function into the complex plane. Its non-trivial zeros lie in the critical strip, between real part 0 and real part 1. The Riemann hypothesis says that every one of them lies exactly on the middle line, real part 1/2. But there is a deeper clue. After adding the gamma factor and the power of pi, one obtains a completed zeta object with a reflection symmetry. S and 1 minus S describe the same spectral information. That symmetry looks less like an accident of algebra and more like the trace of a hidden geometric system. This is the guiding instinct behind many spectral approaches to the Riemann hypothesis. Find the space, operator, or dynamics for which the zeros become natural spectral data. Now for the unfamiliar side. There are exactly 4 finite-dimensional norm division algebras over the real numbers. The real numbers, the complex numbers, the quaternions, and the octonions. Their dimensions are 1, 2, 4, and 8. Each step gains new directions, but loses an algebraic comfort. The real numbers are ordered. The complex numbers introduce a square root of -1. The quaternions become non-commutative. I times j is k, but j times I is minus k. The octonions go further. They are non-associative, so the placement of parentheses can matter. An octonion has 1 real direction and 7 imaginary directions. The multiplication of those 7 imaginary units is usually encoded by the Fano plane. Each oriented line gives a cyclic multiplication rule. Reverse the direction, and the sign changes. Most introductions present this as a multiplication diagram to memorize. But in the 3-seed, the Fano structure is not pasted on afterward. It is read from the geometry itself. The zeta space framework contains a tower of seed geometries. S0 corresponds to the real numbers. S1 corresponds to the complex numbers. S2 corresponds to the quaternions, and S3 corresponds to the octonions. This is not merely a list of labels. The lower seed levels occur inside the higher ones through their cells, faces, seams, and restriction maps. So the geometric descent S3 to S2 to S1 to S0 mirrors the algebraic descent, octonions to quaternions to complex numbers to real numbers. The 3-seed itself is built from 4 2-dimensional orbifold sheets, glued along an enriched seam graph gamma, together with a global symmetry system pi. Each sheet is a football-like Riemann sphere with 2 cone points. The sheets meet along the common seam, producing a compact stratified object that can be visualized inside an octahedral cage. This is important. Gamma is not just 12 bare edges in a combinatorial graph. It carries transport, orientations, local systems, holonomy, and the restrictions of the sheet geometry. It is the enriched common interface through which the whole seed communicates. Here is the crucial piece. The 3 seed has 7 distinguished oriented directions. 3 come from the colored seam families, red, green, and blue. 4 come from the 4 orbifold sheets. 3 plus 4 equals 7. The 7 imaginary directions of the octonions. Choose the seam directions as I, J, and K. Choose one sheet direction as L. Acting on that sheet by the 3 seam transports produces IL, JL, and KL. The 7 directions are therefore I, J, K, L, IL, JL, and KL. But counting to 7 is not enough. The multiplication has to be there, and it is. Label the 4 sheets A, B, C, and D. The 3 seam colors pair them in 3 perfect matchings. Red pairs are with B and C with D. Green pairs are with C and B with D. Blue pairs are with D and B with C. If we forget orientation, these matchings have the Klein-4 pattern. Once the seam transports are signed and cooriented, they lift to the quaternionic relations. Each basic transport squares to minus the identity, and exchanging the order reverses the sign. So the enriched seam carries the quaternionic core. Now allow that quaternionic core to act on the 4 sheet directions. The oriented incidences among the 3 seam directions and 4 sheet directions produce the 7 oriented Fano triples. Read cyclically, each triple says E a times EB equals EC. Reverse the order and the result changes sign. Each imaginary unit squares to -1. That is the octonion multiplication table, recovered from the seam and sheet geometry of S3. The Fano plane is not an external decoration. It is the compressed algebraic image of how the seed is glued and oriented. Nonassociativity now becomes less mysterious. In the octonions, multiplying 3 elements can depend on which pair is combined first. In the seed, composing transports through different seam and sheet routes can pass through different intermediate incidence data. The geometry remembers the bracketing. This does not mean the space behaves randomly. Octonions are alternative. Any 2 elements generate an associative subalgebra. Geometrically, when we restrict to an appropriate 2-direction or quaternionic subsystem, the ambiguity disappears. The lower seed is associative even though the full 3 seed is not. That is exactly what the tower predicts. Real, complex, quaternionic, octonionic. Each level preserves the lower structure while adding a new global freedom. So S3 is not simply a 3-dimensional picture of an 8-dimensional algebra. It is a low-dimensional stratified geometry whose oriented transport laws encode that algebra. So far, this explains why the 3 seed is octonionic. But what does any of this have to do with Zeta? Each of the 4 orbifold sheets has 2 cone points, giving 8 cone local sectors. From a cone point, the geometry expands through a multiplicative dilation coordinate toward the common seam. Locally, one studies modes attached to these cone geometries. Organized correctly, those modes form theta-type data. Theta functions possess a reciprocity exchanging a scale t with its inverse, 1 over t. On the seed, this is interpreted as a passage between cone local behavior and winding or return behavior on gamma. The local modes are transported to the common seam, averaged through the global symmetry pi, and then Mellin transformed. And the Mellin transform of theta data is precisely the classical analytic pipeline that produces the completed Riemann zeta function. Schematically, cone modes theta reciprocity, seam winding, symmetry averaging, Mellin transform completed zeta. The functional equation is therefore not appearing from nowhere. The local scale inversion, t to 1 over t, becomes, after Mellin transform, the global reflection, s to 1 minus s. This is the proposed bridge. The very same 3-seed whose oriented incidence recovers octonion multiplication also organizes the reciprocal spectral data that generates completed zeta. Now we can state the central idea. The Riemann hypothesis may require the 3-seed, not because the zeta function secretly takes octonion values, but because S3 is the first seed with exactly the global architecture needed to hold all of these structures together. It has a quaternionic seam core, 4 additional sheet directions, 7 Fano-organized imaginary directions, 8 cone local sectors, and a rigid global symmetry that relates local reciprocity to the reflection of the completed zeta function. At lower seed levels, pieces of this structure survive, but not the full organization. At the 3-seed level, algebra, geometry, symmetry, and spectral transform meet in one compact object. This also changes how one thinks about the critical line. Rather than treating real part 1/2 as a miraculous vertical line drawn inside the complex plane, one asks whether it is the fixed, unitary locus of a global involution acting on the spectral geometry of the seed. In that language, the zeros should be understood as spectral states constrained by the same symmetry that exchanges S with 1 minus S. There is an important distinction. The geometric reconstruction of the octonion multiplication law from S3 is one part of the framework. The proposed identification of the non-trivial zeta, zeros with the admissible spectral divisor of this seed, is the decisive Riemann hypothesis step. Those statements should not be blurred together. Showing that the seed is octonionic does not, by itself, prove the Riemann hypothesis. What it does is identify a highly rigid candidate geometry in which the functional equation, the critical symmetry, and the prime-sensitive spectral trace can be studied together. The research problem is then sharp. 1. Construct the relevant operator or spectral divisor on S3. 2. Prove that it reproduces the non-trivial zeros. 3. Prove that the seed's unitary symmetry forces that spectrum onto the fixed line. That is where the Riemann hypothesis lies inside this program. So, what do the octonions have to do with the Riemann hypothesis? Possibly this. The octonions are the algebraic signature of the smallest seed geometry rich enough to organize the full zeta mechanism. Their 7 imaginary directions record the oriented seam and sheet structure. Their quaternionic subalgebras record the lower faces of that structure. And their nonassociativity records genuinely global routing information that disappears when we restrict to a lower seed. Meanwhile, the cone modes, theta reciprocity, seam holonomy, global symmetry, and Mellin transform turn that same geometry toward the completed zeta function. The conjectural picture is not that octonions magically solve Riemann. It is that octonion algebra and the Riemann spectral problem arise from one common geometric seed. And if the critical line is ultimately forced by that geometry, then the octonions will not have been an exotic detour. They will have been telling us what the hidden space behind zeta had to look like all along. If you want, in the next video I can build the octonion multiplication table directly from the 3 colored seam matchings, step by step, with no Fano plane assumed in advance.